I'll talk about this integrated software stack for DQC algorithms and their application to industrially relevant aerodynamics use case for today. Right. So this presentation is divided in three parts. First, we talk about the software stack and the ecosystem that enables this entire end-to-end DQC workflow. Then we give an overview of the cloud infrastructure that exposes this, say software stack even to external users. And lastly, we'll see some of the results that we have achieved using DQC today, specifically for aerodynamics use case. Yeah, so moving on. So to start, I'll introduce you to this software ecosystem and the various layers of the stack. The DQC algorithm or differential quantum circuits that first appeared in scientific community as a preprint back in November 2020. Last week, we already had Lorenzo talk a bit more about details of the inner workings of the DQC. And Moritz today already earlier, give you basically a teaser of what this DQCs are. It's basically physics-informed neural networks, but using quantum models as always. Just 6 months after the initial preprint in May of 2021, the paper was published in Physical Review A. At the time, where there was growing interest in near-term quantum algorithms. This was a close and active collaboration between both academia and industry, as highlighted by the authorship as well. One of the co-authors is a co-founder of a quantum startup, the SAID startup. Then would later go on to merge with Pasqal in January 2022. So this is the moment where in quantum landscape was beginning to shift more from merely theory to implementation as well, especially for near-term quantum algorithms, because we do not have fully error-corrected quantum computers yet. But around the same time, the equality project was also being conceived. It's this pan-European effort aimed at building scalable software foundation for quantum computing with a particular focus on industrial relevance. This project was proposed and submitted in 2022 and officially kicked off in November of the same year. At the time, DQC was still largely proof of concept thing. It existed as research code crafted by scientists and used primarily to demonstrate the algorithm on a set of basic equation, the kind of benchmark example typically used in academic studies. But the goals of equality as a project is they're more ambitious. The project is designed to help bridge this gap between quantum theory as it exists in academia and what happens with real world problems in the industry. It aims at developing software primitives that could support the next generation of quantum algorithms, not just for simple tasks, but for solving meaningful problem in physics, chemistry, optimization, and machine learning. We had seen what kind of problems we would want to solve in the presentation earlier as well. With that broader vision, DQC stood out as one of the promising candidates for further development. The financial support provided by Quality Project has been absolutely crucial. It has allowed Pascal to invest significantly in this software stack. One of the major outcome of this effort was the development of this new quantum programming interface, Cadence, as we call it. This is tailored specifically for writing quantum circuits and more geared towards quantum machine learning. And this is optimized for the unique characteristics of neutral atom hardware as well. This cadence then became the foundation for a broader set of tools. Out of this effort grew the Flow ecosystem, and this is a collection of specialized library which are geared towards solving differential equations using the capabilities provided by Cadence. These are designed to support DQC-based experiments and an end-to-end workflow from modeling the physical problems into the differential equations to optimizing them and then solving them. This libraries were built to be modular and extensible, making it easier to prototype, optimize, and deploy a variety of different quantum algorithms in a real world setting. These tools being proprietary, A cloud API was also developed, providing an interface for external partners and customers to access Flow's capabilities remotely via the Pasqal cloud. This allows the users not only to write and simulate these DQC programs, but also to execute them via the cloud through this integrated platform. In this way, you can think of this as what began as a theoretical idea in a research paper has since been transformed using a practical tool chain supported by this dedicated infrastructure and made available to a growing community of quantum practitioners. The story of DQC from its early origin to its place within the Flow ecosystem is a clear example of how this collaborative and cross-sector projects like equality have really helped accelerate this innovation and bringing quantum computer to more practical use cases. Before we look at the PDE specific tools such as Flow and Flow ecosystem of libraries, we have a look at this engine essentially that powers the quantum computations underneath, right? And this is Cadence. The so this is the most user-facing component of this entire stack. Cadence serves as the primary interface for designing quantum circuits. However, further down the abstraction level, we have PyQTorch, which is an open source state vector simulator, uh, which acts as a backend for Cadence. For tackling the breadth and depth of this, real world differential equation problems, more specialized libraries are also required. By integrating Cadence and PyQTorch workflow onto this proprietary tools of methods that we'll soon have a look at, we unlock these capabilities as well. Um, PyQTorch is a crucial component of this stack since it provides a differentiable simulation capabilities. Differentiability allows one to compute gradients of the quantum circuit output with respect to the feature parameters as well as the circuit parameters. Both of this, as you can imagine, are needed for calculating derivatives. In a differential equation, you need to calculate derivatives, but also for optimization purposes. As the name pretty much gives it away, PyQTorch is an integration with PyTorch, or you can think more of it like an extension of PyTorch to quantum operations. PyTorch is this open source and probably one of the most popular and widely used deep learning framework developed by Meta. This enables the utilization of PyTorch's automatic differentiation and optimization tools, further simplifying and abstracting away this entire optimization process. And the modular nature of PyTorch and Cadence allows the users to implement their own quantum or classical models and use readily with the rest of the machinery provided by Cadence. So if you are aware and if you have experience working with PyTorch, you can pretty much translate that experience and also being able to write quantum programs using Cadence. To showcase how Cadence allows the users to define and train a QNN for solving PDEs, I can show you this little example that I've taken directly from Cadence documentation, and I also invite you to try it yourself if you're interested. So Cadence allows the users to specify the kind of different components of the QNN models at a much higher abstract level. For instance, here the user can specify they want a hardware efficient ansatz. So when you see the HEA, that is what it's an hardware efficient ansatz. Thus abstracting away the need to define the individual gates and the operations that form the hardware efficient ansatz. Once the once the user has defined a QNN with Cadence, the training process itself is straightforward, and one would train it like one trains any other PyTorch model. Here, the simple training loop would train the variational parameters in the circuit to best match the PD. In addition to the high level abstraction provided by Cadence, it is also equipped with a suite of tools for quantum machine learning, uh, and in the form of a dedicated package called PerceptTrain. This allows the user to translate variational quantum algorithms into practical executable code and makes Cadence the pretty much the prime avenue for DQC simulations. Compared to its initial version, which was a basic internal tool for designing quantum circuits, Cadence has been extensively developed over the last 2 or 3 years. And during the progression of this equality project, significantly expanding its capabilities for designing and analyzing quantum algorithms in general, but also particularly in the context of quantum machine learning. Um, well, we saw an example, and you might ask, what is the need for Flow ecosystem of libraries at all if Cadence is so awesome? And rightfully so. Although the framework provided by Cadence is, very robust and versatile, and it allows you to design and implement all these quantum circuits, its core functionality is not specific enough for PD use cases. So what we basically need is some specialized tools required for solving complex PDEs. And that is where this Flow ecosystem of libraries comes in. Moreover, to properly, catalog a growing collection of problems and build accessible database of related experiments, and integrating this ecosystem of libraries is needed. These tools and methods, they basically form this coherent form, like a coherent set of libraries. This Flow ecosystem, which is made of Flow equations, and Flow lab. Uh, yeah, so Flow is the primary component of this ecosystem, and it's a library based on Cadence, and it's equipped with the necessary capabilities to robustly solve complex PDEs. So you can think of Cadence as this, I called it an engine earlier, like this engine behind designing of quantum circuits and quantum models of different types. While Flow is this toolbox that equips the user with different optimization schemes, as well as all the different tricks that enhances the performance of both DQCs as well as classical pins. For example, a common practice while solving PDEs, or a common need as such, would be the need to define different domains and subdomains where the equation of this system of PDEs are defined on. Flow makes this process very straightforward. This is not just limited to standard shapes and domains like squares and circles and so on and so forth, but also you can define custom geometries and boundaries as needed for whatever particular physical problem that you're trying to solve. Right. These geometries are then well integrated with the sampling techniques to sample points for DQC workflow. Earlier in Moritz's slide, we saw that within the domain, we had sampled some points. As it turns out, we have learned both from experience with classical and quantum pins that the way you sample and the strategy that you employ for sampling these points does matter, and it will play a role in better convergence or faster convergence. Right. So all these exotic geometries that you define is very well integrated with a variety of different sampling techniques as well. And this helps a lot in overcoming certain pathologies in training pins at large, but also DQCs in particular. For that, one gets to choose from like a standard set of optimization techniques that are specialized specifically for solving PDEs. And just as before, the extensible nature of these libraries means that if the user wishes to define their own optimization routine, then they can do that and use all the other tools that are provided without having to rewrite everything just because they wanted to use one component of it differently. This toolbox is constantly being improved based on the latest research and results, making use of the state of the art, not only from quantum domain, but since pins are extensively used in this scientific machine learning community, then also from classical domain. Such as adaptive loss balancing techniques, which allows automating balancing of the different residual terms which form the overall loss, and so on and so forth. Um, Moving on, this ecosystem only came to be from extensive experimentation. You work with it enough, and you realize these are the needs that now need to be solved more than a basic toolbox. So what this extensive experimentation has revealed over time is that there is a need for this curated library of relevant use cases. What this provides for the user is this readily available catalog of equations of different domains and so on and so forth. This allows us to have a uniform interface for these different equations. And this also allows us to extend tools to a set of equations in a uniform and consistent manner. Furthermore, when we have this level of extensibility at the level of cadence as well as flow, you can imagine how the number of different QNNs and configurations that one can throw at this different problems in our attempt to solve them, that blows up drastically. Which means we also basically need performance evaluation and benchmarking tools. So Flow Lab is what serves this purpose with a suite of experiment tracking and benchmarking tools, and ensures reproducibility of results with a total tracking of performance as well as parameters and hyperparameters of the solvers that we're using. So this was I hope not too boring summary of the tools which powers the solutions. In the next part, we'll look at the cloud API, which is what makes these tools available and accessible to external users as well. Since the Flow ecosystem of libraries is proprietary and closed source, it is made available to the external users via the Pasqal cloud. We have developed an API and a client SDK that allows external users to benefit from all the set of tools that I just talked about. The API is available to the users via Pascal Cloud, which then further interacts with the set of tools. The users can submit jobs and opt-in results, which use the infrastructure that I talked about, starting from PyQTorch, Cadence, Flow Lab, and Flow equations. PyQTorch and Cadence happen to be open source, so you can use them directly. But to be able to use this advanced PD specific tools, you need to use the Pascal Cloud and the API and the SDK. On being able to submit these jobs on the cloud, the user can choose a variety of parameters and hyperparameters. And this is not just limited to the kind of problem that they want to solve, but also specifications of what kind of solver they want to use, and what kind of model they want to use, and they can do this on their own based on their own choosing. Um, by this, what I mean is that in case the user is solving a linear advection problem or a diffusion problem or something like this, the user can specify what the viscosity of the problem is, what the domain sizes are, and so on and so forth. So this is what I meant when I said all the problem specifications the user can define on their own. While on the solver side, the user can specify the size of the circuits to use by specifying the number of qubits, for example, for the to encode time or to encode X and so on and so forth. The user can specify what is the depth of the circuit and so on. And lastly, the user is also able to choose the training parameters, such as the number of co-location points to use. This number of co-location points is what you earlier saw on Moritz's slide, where they were marked by an X. If they want to use supervised data for training and so on. This supervised data is basically the measured data and so on that Moritz earlier referred to. Overall, the nature of the API and the flexibility allows the user to benefit to the maximum extent possible from all the capabilities of the entire software stack that we saw earlier. Moving on and to the last part now, we look at some of the results that we have obtained by running this DQC problems on more aerodynamic specific use cases. So the first problem that we look at here today is this linear advection problem. Well, this serves as a good starting point to test DQC on aerodynamics type problems. It's a relatively new approach. So this is basically the test bed where we try different tools and different approaches. Here in this plot, you can see the performance of the DQC pin compared to the reference solution. The solution here was obtained using a QNN with 4 qubits and a depth of 3 hardware-efficient tensor layers. As you can see, it achieves a high accuracy at all times across the domain. Uh, Now, for the next part, we look at a more complex problem, right? Like solving a simple linear advection problem is not enough, right? In the beginning, we said industrially relevant and so on and so forth. So the problem that we face in industrial space are far more complex than a simple linear advection problem, which already happens to have an analytical solution if you wanted, right? One such problem that we look at is that of a fluid flow past an airfoil. This might look very similar to you since earlier when Maurice was presenting the work of Alvana and Lois, he also showed us an airfoil. In this case, we consider this, NACA 0012 airfoil, which is among the standard shapes that are used for testing and prototyping. The the case that we consider here is that of a constant, steady inflow parabolic velocity profile. So what all of these words mean is that here is the inflow. So here is where the fluid is flowing from, and what is guaranteed or what the problem states essentially is that here there's a parabolic velocity profile. What I mean by that is that the velocities are zero here, and it goes parabolically like this. So it's basically maximum in the middle, right? Uh, what you see on the left is the reference solution obtained using finite element methods, while the one on the right is the one using DQCs. As you can see, the solution, although captures this qualitative shape to a degree, is slightly off quantitatively. Uh, the bar should also reveal that much. Well, a Navier-Stokes problem is known to pose, not just one, but a variety of problems for pin-based solvers. And I say pin-based because this is unfortunately not limited to just quantum-based solvers and DQCs. This is also true if you're using classical pins. This Some of these problems are well known and well documented. This happens in the form of collapse to a trivial solution in the interior, failure to propagate any boundary conditions away from the boundary into the interior again, and so on and so forth, right? But with a variety of tools that I alluded to earlier and talked about some of them, when with extensive testing, we are able to make progress towards a solution that is much closer to the reference solution, even for a complex industrially relevant use case. So, and yeah, all of this has happened over the duration of the equality project as well. I think that's it from my side for now.